started on, first of all, the lot. We were, the way the lot is situated, it runs north-south. So that gave us the challenge of designing the house that had appeal from the road, but could also take full advantage of the southern exposure.
The orientation of the house on the site is most important in any situation, because you want to look at what rooms are going to face what direction as the sun moves through the day.
So this is our solar needle. This is what we use on sites to figure out where solar south is. What we're doing is measuring the shadow. When the shadow is at its shortest is when the sun is at its highest, and that is solar noon. So we will be checking as we go here. We know from our devices that it's going to be around, this time of year is actually going to be around close to 12, but we're going to check, and when that shadow is at its shortest, we know that's solar south, and we're going to pull a parallel line through our shadow, and that's going to set our north-south. So this is just an old window weight, which is kind of fitting because, you know, solar in windows is huge. That's where we want to gain, you know, grab our solar gain is through the windows. Plus, it's really heavy. So we use it, you know, there is a slight, even with the wind out here today, it's moving a bit, but it's not too bad. It's more than accurate enough. So we essentially, you know, we can watch and we can just start marking, you know, the length of the shadow. Using the shadow as well as our apps, we know we're close. So what the guys are doing, TJ and Jeff are doing with Adam, is pulling a string through the center of our shadow. So this string, this shadow pointing solar south, is going to set our string dead on solar south. You guys are bang on there. Is that the time, Brent? All right, that's it, guys. You guys are right through the center, Jeff. We're going to create a right angle triangle off of this north-south line to go run east-west. We try and use everything we can to use less, and as the homeowners, they use less because it all starts in the design of the house. So that's why, for us, this is very important.
You have also criteria, in our case, we have to follow that takes us to the Nottawasaga Conservation Area, where we have to work with the requirements that they put forward in terms of elevation, floodplains, the amount of fill we have to bring in, a number of criteria that they set forth that we had to accommodate.
And I think as a builder and going through the process of permitting, you know, working with the conservation authorities can be seen as a challenge, or can be seen as almost a thorn in the side with delays. But the reality is that when we're done the project and we've complied to their guidelines, we are building a house that is resilient to, you know, the 100-year flood. Definitely being you know, aware of the water table is you know, MVCA has helped us with that.
Well, that did become part of our challenge. Yes. Because we dealt with the fact that first we were going to do a basement, then they said no basement, then they said we have to do a slab on grade because of the water levels, and then eventually if we were able to raise the house out of the ground, then that brought the basement up, so we were allowed to have the basement again, so we could have a granny flat or a potential living quarter downstairs, which was, it made us explore other aspects of the house that we may not have ever done until we were challenged with the problem, right?
This lot is governed by the Nottawasaga Conservation Authority, so they set us an elevation based on a 100-year flood. So what we're doing is we're building our house to the MVCA's guidelines that is going to elevate our house so that, you know, if we have the 100-year flood, this house is going to will be fine. That is, we have to be 1 meter above the crest of the road. So we're going to, with the transit, shoot the crest of the road, transfer it to our grade stick, And with off our drawings, we're going to, we'll know the elevation of the house based on that. And then that's it there. So from that mark, we're going to work off the drawings, do our math, and set the top of the foundation, and then from the top of the foundation, we're going to work down to the underside of our footing. All right, so this is what we have. So what we've done with the laser is we have transferred the crust of the road to our grade stick here. Again, that it's attached to the telephone pole as it won't move. So this is our road mark. And what MVCA is telling us is that our lowest opening, which would be the bottom of our basement window, has to be 1 meter above the crest of the road. So what that does is this brings the bottom of our basement window to this point. Our windows are from the underside of our basement window to the top of foundation is 3'6". So we've taken this from this mark, we've come up 3'6", and that now is telling us the height to the top of our foundation. Our foundation wall, including the footing, is 9 feet from the top of our foundation. So from that mark, we'll be able to set the elevation of our footing.
House basically just works for itself. It lets the sun come in, it heats, in our case we have a masonry wood stove, it'll heat that thermal mass of rock, and that then later in the day that emits the heat back into the house. We will use reflective paint, radiant paint, which will also help reflect the warmth back into the house, and in the winter and in the summer it helps to dissipate. The number of windows that we put in the house is going to be relative to how much heat is also entering through those windows and how much heat is lost in the winter. So all these proportions and percents of openings and thickness of walls and insulation and slopes of roof and any kind of materials that are absorptive and can then hold the heat in the daytime and then emit it at night back into the house are all positive and important aspects of a passive solar design.
And I think it's important to your points, Donna. It's about, one thing is about orientating the house to the sun, but it's also looking at, again, when you say glazing, so we're 15% on the building envelope with glazing, and 50% of that 15% is on the south side. So again, the way the sun works in the summer, and so then we have oversized overhangs on the roofs as well. And the reason they're there is in the summer our sun sits high, so the overhangs will shadow the sun from coming into the house. So that'll stop the heat gain. In the winter, the sun is at a much lower elevation in the sky, so that, again, to your point, will bring in the heat. So in behind that, we do have Rockwell R22 in behind there, and now we've applied this, and before mechanical. Traditionally it's done after mechanical is completed, but because we have a double wall construction, our 2x4 wall is our mechanical wall. Anything mechanical is going to come up through that interior wall, so nothing will penetrate unless it's an exterior electrical or vent. An exhaust vent will not penetrate through. We've used a sealant to the floor system to seal it, and then as we've run our main wall barrier up, we've sealed it as well.
One of the other values that we have specifically regarding this non-structural interior wall system is that it's found inside of the control layers here for air and vapor. So if there are any requirements after the fact by a homeowner to run any other cabling or electronic data assemblies, what have you, they're running that inside of the control layer itself. So there's no potential for penetrating or breaking this and creating issues with either condensation resistance or moisture movement.
So with the process here, what we'll do, instead of using shims all the way around, we are going to use these window setting screws, and then we'll use a backer rod to seal on the furthest outside edge, and then we'll spray foam in there, and then we'll use a pink bat insulation to chink in there, and then we'll end up using another Siga product from our vapor barrier membrane to seal to the jamb.
This is substantially different than anything that the production industry or the standard custom home builder would be doing, from a materials perspective as well as from a sequencing and detail perspective. So it's not consistent with what we would see. It's a step above.
We know that air leakage is associated with increased energy bills, so the less air leakage we have, we can expect our heating bills to be lower. They're tied together. Another reason why we want low air tightness is that air leakage brings moisture with it in the air, and that can lead to decay of framing members, or it can lead to rot.
This becomes a very visual test, a test that allows us to share information readily in terms of areas that maybe weren't properly detailed or areas that might have been missed initially through the team. And it creates a learning potential, I think, for the guys to really, next time they're doing this, think about the results they saw here. And I think part of this is continual improvement, the process improvement that's part of building better homes.
There looks like a slice in the vapor barrier up here, just where someone missed some tape. We'll have to patch that up.
Generally speaking, we're looking at sort of from large to small, we're looking at sort of the major penetrations in the building enclosure. And those could be looking at windows and doors, which generally are the largest in terms of the complete straight through penetrations. And then any mechanical penetrations, any stacks, any plumbing fixtures that go straight through into the enclosure or through the enclosure. And then also things like external lighting, where we have switches on the outside or lights around entry doors. These areas where wiring is going through also tend to be key areas of potential infiltration or exfiltration of air.
So this is the electrical wiring that's going to go to the lamp fixture on the outside of the building. And of course the electrical wiring has to come into a plate here so we can turn the light on and off. Well, that's a relatively thick wire, and it's penetrating the house. It's actually going through the wall. In fact, this is a double wall house, which you may or may not know from previous videos. But so this is a hole that's going to go all the way through the wall. What does that do? Look how they've sealed it. So it goes all the way through. They've sealed it on the outside, they've sealed it on the inside. Not only that, they've caulked around where the air barrier is on this penetration, and then they've taped around.
A substantially airtight house, better than code or substantially better than code, could see 10 or 12% increases or enhancements.
So we are all set up to do a final air test for this house. We have the fan set up on the door to do a blower door test. That's going to measure the air leakage across the envelope of the house, meaning the exterior walls, in order to measure the air leakage across it. And then it's going to give us a final number in terms of ACH, or air changes per hour. The code allows you to have 3.0 ACH if you are testing, and then if you're not testing, it's an assumed 2.5. So we can kind of use those two numbers as like the max ACH that we want to try and target to be below. And so yeah, we're gonna see what we're at now. Today we're really doing it to see what the air tightness is, again, across the exterior envelope of the building. Why that matters is for homeowners, if we have a lot of air leakage, that translates to heating bills. So how much does it cost to heat the house if we're losing that warm air? Another reason that we would want it is just to make sure that we don't have failures in the building assembly. So if we've got a lot of air leakage, that could lead to water coming in, that could lead to degrading of wood members or to rotting. So we want to make sure that we don't have, on a production home standpoint, a lot of callbacks or any issues down the line for the person who's actually going to be occupying the home. And then we want low enough air tightness so that we can really make our mechanical systems be the ones that are taking care of the ventilation. So we just finished, and the final air tightness score was 1.82 CH. And so, like I said before, when we are testing the houses, then the code wants us to be below 3.0 ACH.
Right.
So you're obviously well below that.
Right.
Your CFM 50 number went from being above 1,000 to being just below.
Right.
And I think it fluctuated when we did that previous test.
Right.
And there are still some things that aren't done, like all of the trim that isn't done
Right.
within the house, that'll cut it down a little bit more.
Right.
But really at 1.8 ACH, that's low enough that you're not worried about homeowner callbacks. We didn't find any really big holes. That's really the purpose.
Right.
You're not going to be worried about heating bills. It's going to be
Right.
comfortable to live
Right.
in this home. So you've
Right.
really met the requirements of the code, exceeded them, and then you've guaranteed whoever's going to be living in the home that they'll have a comfortable home to live in.
Right. Okay, well that's great. I mean, that's what we were aiming for. So.
We have 8 different categories that we consider when ranking our products. So the first one is healthy home. So healthy home considers off-gassing VOCs, if any of these products are doing this. We want to make sure that we include products that don't off-gas or have as little VOCs as possible, because chronic exposure to these is actually unhealthy. The second category that we consider is if the products have low embodied energy and a low life cycle impact. So really what this means is whether the materials from harvesting to manufacturing and transportation, how much energy is actually used to do this, because what we don't realize sometimes is that products that are made overseas and stuff actually carry a lot of, or use up a lot of energy that we're unaware of. So we really want to make sure that that's limited. Life cycle impacts. Some people will get a product and don't realize the energy it takes to actually run that product, or the maintenance on that product. So we want to make sure that the life cycle impact of the stuff that we're using will be for the long run, and won't cost them a lot of money and won't cost a lot of energy to maintain. This kind of goes into our next pillar, which is durability and resiliency. What we see a lot in construction nowadays is cheap materials and cheap finishes being used because they look nice, but what people don't realize is they don't last that long. You might have to replace them after 10, 20 years. And when you're replacing them, you're now going back through that whole manufacturing process. You're going back through all that embodied energy it took to make those again. So spending a little extra money on products that are more durable and that are more resilient are better for the environment and better for the consumer. Another thing tying in with life cycle impact is locality. So what we try and do is we try and source our products as close to the job site as possible. Ontario is where we try and get most of our products, but if we can't do that, Canada, then the States, we try to not use products from overseas unless there are really good reasons. So another thing that we like to focus on is using reclaimed and salvaged materials whenever we can. So we actually go out and source materials that we can use. One example would be the fireplace that we have in the living room. That stone was actually reclaimed from a foundation in Toronto, which actually originally came from the Humber River. So we like to include pieces like this throughout the house to make sure that there's some story and some history within our buildings. So we strive to use products that can be recycled or can be reused in a different way. after they're not needed anymore. So we stay away from products that will go straight to the landfill as much as possible. Sometimes it's not possible, but we really consider that and really take that into consideration when we're choosing products. So our last pillar would be our Biophilia Pillar. This pillar just is used to see if there are connections that we can make between nature and the homeowner. It is shown that there are physiological, psychological, and cognitive benefits of being exposed to nature. So this simply could be exposure to stones, woods, views, and greenery. So we just try to see if we can include as much of this in the house as possible. So although this rating scale is very descriptive and very detailed, it is only a guide. We really need to go through each and consider each when comparing products. For example, our Sika tape that we use, it's extremely expensive, but the reason it's expensive is because it's so durable, because it's so resilient, and because it's adding to the envelope and the building envelope and the efficiency of the home. So even though it might score lower on an affordability pillar, it actually brings so much more value to that. So we'd have to go through each and compare each for each category, for the roofing, for the flooring, etc., to be sure that the product we're choosing has the values and has the characteristics that we value most. Keto Construction just wants to build better, and this rating scale is really helping us do that.